Today we're going to talk about binomial probability. Binomial probability is where an event has only two possible outcomes. One example is flipping a coin. The outcomes are heads or tails. Another event that has as binomial probability, shooting a basketball. The outcomes is you either make or miss the shot. So let's suppose you are told to shoot a basketball 2 times. What is the theoretical probability of all possible outcomes? Well, here it's binomial probability, so the probability of making one shot is 50%. And what are the possible outcomes? What are the things that we could accomplish here? We could either make 2 shots, we could make one of the 2 shots, or we could make 0 shots. So let's look at a tree diagram to demonstrate. Taking the first shot, you're either going to make it or miss it. Then you will take another shot after you make, or another shot after you miss, which represents shot number 2. And then the path where we have 2 makes is along this path here. And then make, miss, or miss, make represents making 1 shot. And then 2 misses represents making 0 shots. Well, if we look at how many outcomes there are across the bottom and how many outcomes there are for each of these possible scenarios, we can find the probability. Making both shots is 1 out of 4. There are 1, 2, 3, 4 possible things that could happen according to the tree diagram, and making 2 shots is one of those 4. Making 1 shot will occur 2 out of 4 times, which also equals 1/2, and then making 0 shots is 1 out of 4. Let's look at the parallel between our answer and Pascal's triangle. Pascal's triangle is a pattern that has been created a long time ago. And here we can take this pattern, we can take this triangle, and we can determine binomial probability based on the rows of the triangle. So the first thing that you want to do is, in order to get the denominator of our probability, we need to add across. Okay, so if we're taking 1 shot, then we're either going to make it or miss it, and it's a 50-50 probability, or 1 out of 2. Each entry, each individual entry represents the numerator for the probability of the best possible outcome to the worst possible outcome. And then each row represents the total number of events. So let's use Pascal's triangle to solve the previous problem. Again, suppose you're told to shoot a basketball 2 times. What's the theoretical probability of all possible outcomes? Remember that possible outcomes are making 2 shots, making 1 shot, or making 0 shots. Well, from the previous picture, we saw that this row right here is whenever you're taking 2 shots. So whenever you add those up, it's a total of 4. So our denominator for each of our probabilities is going to be 4. And then making 2 shots is the first outcome. That means it's the first entry. So that's 1 out of 4. And that's what we got earlier. Then the second outcome is making 1 shot. That's going to occur twice, which is 2 out of 4. Again, remember, that reduces down to 1/2, but 2 out of 4 comes from right there. And then making 1 shot, or making 0 shot, excuse me, is the last entry, occurs 1 out of 4 times. So we can use Pascal's triangle to find the theoretical probability of binomial events. So let's suppose you flip a coin 6 times. You need to use Pascal's triangle to calculate the theoretical probability of all possible outcomes. All those possible outcomes are listed here. You're either going to get 6 heads, 0 tails, 5 heads, 1 tails, 4 heads, 2 tails, 3 heads, 3 tails, 2 heads, 4 tails, 1 heads, 5 tails, or 0 heads and all 6 tails. So we're going to flip a coin 6 times. You'll notice that this row right here represents the number of shots, number of flips, number of events that's going to occur. This row represents the number of events. So since there's 6 events, we're going to circle that row there. And whenever you add up all those numbers across that row, you're going to get 64. 64 is your denominator. So now we can figure out the probability of each of these possible outcomes. So if we take each entry, starting with the best possible outcome, if we're looking for trying to get heads as many possible times, that's 1 out of 64. 5 heads and 1 tails, that's the next entry. That's 6 out of 64, and that will reduce to 3 out of 36, which I believe will also reduce to 1 out of 12. I'm sorry, it'll reduce to 3 out of 32, which will not reduce. The next entry, 4 heads and 2 tails, that entry is 15 out of 64. I believe that one will not reduce. Then we have 3 heads, 3 tails. That's going to be 20 out of 64. That will reduce down to 10 out of 32. I'll reduce again to 5 out of 16. Then we have 2 heads and 4 tails. Is 15 out of 64. One heads, 5 tails, 6 out of 64. And then 0 heads, 6 tails, 1 out of 64. You should also see that the probability is going to be the same for equal and opposite events. 5 heads, 1 tails is the same as 1 heads, 5 tails. They're the same type of outcome, they're just exactly opposite. Again, you'll see it again with the 6 heads, 0 tails, 0 heads, 6 tails. Those have the same probability. You'll also see it with 4 heads, 2 tails, and 2 heads, 4 tails. Those are equal probabilities, theoretically, because they're exactly opposite events. The last thing I want to do is solve this type of problem with Pascal's triangle. We got the 6th row because we're still flipping a coin 6 times. And I want to see what the probability of flipping heads at least 4 times would be. Well, at least 4 times. Well, this is 6 heads, 5 heads, 4 heads, 3 heads, 2 heads, 1 heads, 0 heads. And then the corresponding amount of tails you just subtract from 6. So at least 4 means 4 or more. Well, here's where 4 heads is. So that's 15 out of 64. 5 heads is more than 4, so it checks out here. So there's 6 of those that occur. And then 6 checks out as well. So there's 1 of those. That means our probability of flipping heads at least 4 times is 15 plus 6 is 21 plus 1 is 22 out of 64. If we reduced it, it would be 11 out of 32. Alright guys, that's binomial probability.